All right, welcome back. I hope you took a nice break there. As you can see, I'm totally, actually it's another decade. I just kind of look the same. So what we've done is we've laid out sort of the general idea of a Markov process, Markov system, and also a hidden Markov model. And what I want to do now is talk about sort of three computational problems of hidden Markov models, and then we'll talk just about a simple application of this to computer vision. Also, just as a word of note, I am not going to go into the detail of different parts of lots of the math, just one part of it, and then the rest I'll, as they say, leave it to the reader or the viewer as an exercise to go get schooled up in it. Because the details were less important than knowing that it could be done, and then it was applied to computer vision. All right, so we have a hidden Markov model, and we said that our hidden Markov model is lambda is a triplet of A, B, and pi, where A is the transition probability, B are the emission probabilities, and pi was just the distribution of where things started. Well, given that a HMM, given a machine, there are three computational problems we can look at. And the first one is this. Basically, given some observation sequence, okay, so remember, O1 through O cap T are the observed outputs from 1 to cap T, so that's a particular sequence, you could ask, what is the probability P of O given that machine? That is, what's the likelihood that that machine generating that particular sequence? And this is really the classification recognition it says problem, but actually how you use it for that, right? Assume I've got a couple different HMMs, maybe three of them, and they each represent an activity, and let's assume that the prior of which activity is going on are equal. All right. So then if I have the priors are equal, all I care about is the likelihood of the data given the model. And the HMM would allow me to evaluate the likelihood of the observed sequence for each of the given models. Whichever one was highest, that would be the one I picked. That's a generative model like we talked about before. So the evaluation problem is, in some sense, the key problem at runtime. It's one we'll actually talk about. Another problem is what's called decoding the sequence. So remember, you have a sequence of observations, and the question is, what's the single most likely sequence of states to have generated that sequence of observations? So it's not all possible ways these observations could generate it. It's just the single most likely sequence, sometimes called the decoding problem. And sometimes you care about that, sometimes you don't. When you do, it basically has to do with saying, well, if the states have some particular meaning to me, right? Remember we talked about sunny, rainy, cloudy, so they might have some specific meaning. I might want to say, okay, here's what I think the underlying state sequence is. Actually, sometimes in genome work, et cetera, they actually want to know what the underlying state sequence would be. But if you're actually just doing it for recognition, then that's in some sense less important. And then the third problem is in some sense the most complicated problem, and that is, okay, I give you a bunch of training examples, a bunch of these O sequences, train a model, learn the lambda, that, and the way you learn it is you pick the one that maximizes the likelihood of getting that observation. It's a maximum likelihood method. It's actually called EM, expectation maximization, and we'll talk about that just a little bit. We won't actually do the math of that part.